Hello everyone, I'm Rain from Team Holium, and we're going to discuss about understanding how mole becomes the bridge of macroscopic and microscopic worlds. So our topics, which will be discussed by myself and my group mates, include mole, atomic mass, atomic weight, isotopes, and stoichiometry. So let's start with moles. So first, a short history regarding this mole. So Lorenzo Romano Amedeo Carlo Avogadro, Count of Quaregna and Cerreto, was an Italian scientist. He is known for his contributions in molecular theory, particularly Avogadro's law and Avogadro's number. The mole was named after Avogadro because he was the first person who thought of it, but unfortunately, he was already deceased when the mole was proven to be right. So Avogadro's number, also known as the mole, has the value 6.022 times 10 raised to 23. It is an SI unit of measurement and is often denoted as N sub A. So it is the number of units in 1 mole of any substance. So the quantity amount of substance is a measure of how many elementary entities of a given substance are in an object or sample. So the elementary entities that can be represented in moles can be atoms, molecules, monatomic or polyatomic ions, and other particles such as electrons. The mole concept is a convenient method of expressing the amount of substance. Any measurement can be broken down into 2 parts, the numerical magnitude and the units that the magnitude is expressed in. For example, when the mass of a ball is measured to be 2 kilograms, the magnitude is 2 and the unit is kilogram. So when dealing with particles at an atomic or molecular level, even 1 gram of a pure element is known to contain a huge number of atoms. This is where the mole concept is widely used. It primarily focuses on the unit known as a mole, which is a count of a very large number of particles. So the number of moles of a molecule may not always be equal to the number of moles of its constituent elements. For example, a mole of water contains N sub A numbers of H2O molecules. However, each water molecule contains 2 hydrogen atoms and 1 oxygen atom. Therefore, 1 mole of H2O contains 2 moles of hydrogen and 1 mole of oxygen. So, for example, how many moles of iron are present in a pure sample weighing 558.45 grams? So, to get the moles, we first have to get the molar mass of iron. So, all we have to do is divide the given grams of the sample by the molecular mass to get the moles. So here the grams will cancel and the moles will be retained, which is why we get 10 moles. Okay. Now you can try this exercise. You can just pause the video if you want to answer. So if you get the answer 12.044 times 10 raised to 23, then you are absolutely correct.
Atomic mass is basically just the mass of an atom. It can be calculated with the help of subatomic particles such as electrons, protons, and neutrons in a given atom. So it is important to remember that electrons or mass of electrons are ideally considered to be part of the atomic mass. However, due to its very small size, electrons' mass is often neglected and also considered to be almost weightless. So we can only focus on the number of protons and neutrons in the nucleus. So for example, in the carbon-14 isotope, since the carbon has an atomic number of 6, it is equal to the number of protons as well. And we can have 8 neutrons to have the total of 14 as its atomic mass. Thus, by definition, atomic mass is the total number of mass of protons and neutrons in the atom, and also referred to as the mass number. Now, we have always come across cases where the atomic nucleus has an equal number of protons and neutrons. For instance, for helium, we have 2 protons and 2 neutrons to have 4 atomic mass, and lithium, we have 3 protons and neutrons to have atomic mass of 6. Now, the question is, does the charge of the atom increase or decrease with the presence of additional number of neutrons in the atom? Try to also answer this question. Identify the number of protons and neutrons in a given element for boron 11 and chlorine 37.
Good morning, everyone. I am Anilo Ita Bernilia from Team Homew, and I will be discussing about isotopes. So, we all know that a particular element, for example, carbon atoms, all have the same atomic number. So, this atomic number is equal to the protons, the number of protons, and these protons determines the element's identity. So, as we can see, every element in the periodic table has a unique uh, atomic number. For example, carbon has an atomic number of 6, oxygen has an atomic number of 8, and hydrogen has an atomic number of 1. So, to recap, subatomic particles of an atom are protons, neutrons, and electrons. Protons that has a positive charge, neutron which has no charge, and electrons that has a negative charge. And protons and neutrons make up the nucleus of an atom. So the electrons contribute to the charge of an atom. Uh, since the proton determines the element's identity, uh, the, the removal or the addition of electrons is the one that determines the charge of an atom. So that's a quick recap. And then the number of protons and neutrons are the one that contributes to the mass number of an atom. So these two are the only one considered since electrons mass is too little to be considered. Okay, next. So to discuss again, isotopes are atoms that have the same atomic number but have different mass numbers. So in the picture, X is denoted as the chemical symbol of the element, Z is denoted as the atomic number of the element, and A is the mass number of an element. So we'll take note again that the addition of numbers of protons and the numbers of neutrons is equal to the mass number. Now that we know this, what exactly are the difference of atoms that are isotopes of each other? So in the slide shown, we can see that there are three isotopes here of carbon, which is the carbon 12, carbon 13, and carbon 14. Um, these uh, these 12, 13, and 14 are the mass numbers, and they all have the same atomic number since that is the carbon's carbon's atomic number. So in order for us to calculate the number of neutrons in these atoms, we can use the formula from earlier, which is the uh, formula for the mass number, and just transpose some of it or transform it into this. So number of neutrons is equals to mass number minus atomic number. So calculating that will result to here. Uh, the carbon 12 has 6 neutrons, carbon 13 has 7 neutrons, and carbon 14 having 8 neutrons. So for a follow-up problem, I want you to answer this. So how many protons and neutrons are in A X that has a mass number of 11 and atomic number of 5? Y where there is 41 mass number and then atomic number of 20, and Z that has a mass number of 131 with atomic number of 53. So you may pause and comment below. Thank you.
So it was previously discussed that the mass of an atom is usually counted by the number of protons and neutrons. But what if there are elements that exist in many different forms? Maybe some are lighter, maybe some are heavier, some are more abundant, and some are less abundant. So in order to debunk that confusion, we're going to talk about the atomic weight. In quicker terms, the atomic weight is actually what we call as relative atomic mass, formally defined as the mass of isotopes of an element with respect to its standard. It is also dependent on the percent abundance of each isotope present in nature. The relative atomic mass is also the ones that are presented in the periodic table. So for example, carbon has a relative atomic mass or an atomic weight of 12.0107. So it has been shown in 2 units, in Daltons or dA and AMU, or I think you're the ones who answer that, or the atomic mass unit. So coining the concept of atomic weight has been a short history. It all started when John Dalton coined that 1 unit of hydrogen is the standard of all atomic scales. However, J.J. Berzelius coined that 1 unit oxygen is equivalent to 100 units of atomic weight. Then it was further debunked by J.S. Stas, wherein he proved that oxygen is usually 16 units per mole or 16 grams per mole because of quantitative analysis. This is emphasized because oxygen is actually 16 grams per mole, and it is accepted until today. Then, because of that proof, the first atomic scale was introduced wherein all nucleic masses or masses in the nucleus are 1/18th mass of ground state oxygen. However, one of the major red flags here is that natural oxygen has 2 more isotopes wherein they are slightly heavier than 16 grams per mole. So this caused a lot of confusion within the scientific community, especially to that atomic scale. So in 1960s, they have decided that atomic weight and the atomic mass will be based from the 112 mass of carbon-12. This is because the other existing isotopes of carbon are slightly heavier or slightly lighter than the most abundant one. Since then, IUPAC is starting to publish uncertainties, or rather the average atomic masses in all elements, including in the modern periodic table. It started when they introduced it in sulfur and the rest of the elements. So let us now discuss an example of the concept of relative atomic mass. You may actually pause this video to try to answer it because it is pretty easy. But we're going to answer it together anyway. So example, the isotopes of bromine, namely bromine 79 and bromine 81, were identified experimentally. So given this table are the respective masses and the respective abundances of bromine 79 and bromine 81. Now, we are asked to determine its average atomic mass. So we have seen here, bromine 79 has a mass of 78.9183 AMU with an abundance of 50.69%, and bromine 81 has a mass of 80.9163 AMU with abundance of 49.31%. So actually, it is easy. So the average atomic mass is usually calculated by getting the average mass of one isotope and the average mass of another isotope. So each weight of the isotope will be the mass of that isotope multiplied by its abundance and the other isotope multiplied by also its abundance. So in the case of bromine 79 is counted as 78.9183 AMU multiplied by 50.69% or 0.5069 added by the mass of bromine 81, which is 80.9163 multiplied by 49.31% or 0.4931. Sum it up together, the two of those values, and we are going to get 79.90 AMU, which in fact is pretty accurate to the periodic table wherein they stated that bromine is about 79.9 grams per mole. And that is it for atomic weight. Here are the reference for this review. And now we're going to proceed to talk about isotope.
Good day, I am here to present stoichiometry. Stoichiometry is the section of chemistry that involves using relationships between reactants and or products in a chemical reaction to determine desired quantitative data. Stoichiometry came from the Greek word stoichein, meaning elements, and metron, meaning measure. Stoichiometry, therefore, literally translates into the measurements of elements. But before we do our calculations in stoichiometry, we first need to have a balanced equation. So let's review first what is a chemical equation. A chemical equation is a shorthand notation to describe a chemical reaction. Just like a chemical formula, a chemical equation expresses quantitative relations. The reactants usually appear in the left sides of the equation, while the product appears on the right side of the equation. We also see stoichiometric coefficient that tells us the number of a certain molecule, and subscripts which tell us the number of a specific element in a particular molecule. It is important to remember that in balancing chemical equations, we only change the stoichiometric coefficients because changing the subscript means changing the identity and properties of the molecule. In balancing chemical equations, we need to follow the law of conservation of mass, which means that the elements present in the reactant side of the equation should also be present in the product side. It also means that the number of individual elements in the reactant side must also be equal to the number of individual elements in the product side. As an example, the reaction of sodium with water to produce sodium hydroxide and hydrogen gas. Two sodium atoms and 2 moles of water creates 2 moles of sodium hydroxide and hydrogen gas. The number of sodium, oxygen, and hydrogen in the reactant is the same as the number of sodium, oxygen, and hydrogen in the product side. This is an example of a balanced equation. As another example, sodium hydroxide reacts with phosphoric acid to form sodium phosphate and water. Here is the unbalanced equation. Let's try to balance out the equation. You can pause the video if you want. But if you want to know the answer, let's move on to the next slide. So to balance the equation, we must add a stoichiometric coefficient to sodium hydroxide to balance the amount of sodium on both sides, and then add a stoichiometric coefficient to water to balance the adjusted number of hydrogen and oxygen on the reactant side. So there's going to be 3 moles of sodium hydroxide and 3 moles of water to balance the equation. Next, we have the limiting reagent. By using stoichiometry, we can determine the limiting reagent in a chemical reaction. Limiting reagents are the chemical species that get used up first and limits the amount of product produced in a chemical reaction. We can quickly determine the limiting reagent by dividing the moles of the reactant over its stoichiometric coefficient. The reactant with this resulting value is the limiting reagent. So continuing our previous example, if 35.6 grams of sodium hydroxide is reacted with 30.8 grams of phosphoric acid. What is the limiting reagent? So first we obtain the moles of each reactant by multiplying the given mass of each reactant by their individual molar mass, then later dividing by their stoichiometric coefficient. Here the limiting reagent is sodium hydroxide because it has the lowest value obtained, which is 0.2966. Next is theoretical, actual, and percentage yield. Knowing the limiting reagent will help us calculate the theoretical yield. The theoretical yield is the quantity of the product assuming the complete conversion of the limiting reactant into the product in a chemical reaction. The actual yield is the amount of product actually produced when the chemical reaction is carried out in an experiment. And the percent yield of a product is the ratio of the actual yield expressed as a percent. So continuing our previous example, if the reaction produced 41.43 grams of sodium phosphate, what is its percent yield? So to obtain the theoretical yield, we need to use the moles of the limiting reactant and multiply it to the ratio of stoichiometric coefficients of the product to the reactant and to the product's molar mass. So the actual yield here is 41.43 grams and the theoretical yield is 48.63 grams. To obtain the percentage yield, it's the actual yield over the theoretical yield times 100%. So 41.43 grams over 48.63 grams times 100 is equal to 85.19%. So next is excess reactant. Excess reactant is the reactant present in an amount in excess of that required to combine with all the limiting reagents. To determine the mass of the unreacted excess reactant, we simply calculate the mass of the reacted excess reactant using the mass of the either limiting reagent or product and subtract it from its given mass. So using the mass of the obtained product, we obtained the reacted excess reactant, 29.06 grams of phosphoric acid. So to determine the mass of unreacted phosphoric acid, we just simply subtract it from its starting mass, which is 30.8. So 30.8 minus 29.06 is equal to 1.74 grams of unreacted phosphoric acid. Next is the percent composition. Percent composition is the ratio of the amount of each element to the total amount of individual elements present in the compound multiplied by 100. Using the formula number of atoms times atomic weight all over the formula weight of the molecular compound times 100%, we can determine the percent of element. And using this formula, determine the percentage of mass of carbon in ethane or C2H6. You can pause the video if you want to solve it. But if you want to know the answer already, let's go to the next slide. So the percentage of carbon in ethane, following the equation, since there's two carbons, we will multiply it to its atomic weight, which is 12.01, and divide it with 30.068, which is the formula weight for ethane, times 100, and it will be 79.89%. Therefore, ethane is 79.89% carbon by mass. Next, we are going to discuss about empirical formula. The empirical formula of a chemical compound is the simplest whole number ratio of atoms present in a compound. There are a few ways to determine the empirical formula of a compound depending on what is given in the problem. If the given is the percentage mass, then we can assume 100 grams and convert the mass percentage of elements into grams of each element. If grams of each element were given, we can use the molar mass to convert them into their individual moles. And if the moles of each element are given, then we can use the mole ratio to determine the empirical formula. So as an example, the compound para-aminobenzoic acid or PABA is composed of 61.31% carbon, 5.14% hydrogen, 10.21% nitrogen, and 23.33% oxygen. Find the empirical formula of PABA. So since the given here is the percentage composition, we are going to assume 100 grams and convert those percent compositions into grams of individual elements. So after we obtain or convert the percent composition to grams, we are going to multiply those with their individual molar mass to obtain the moles. After obtaining the moles, we are going to obtain the mole ratio by dividing the smallest number of moles, which is from nitrogen, 0.7288. After we obtain the molar ratio, we are going to use these values to formulate the empirical formula. And the empirical formula for PABA is C7H7NO2. Now, for you to solve, determine the empirical formula of a compound that contains 0.799 grams of carbon and 0.201 grams of hydrogen in a 1 gram sample. You can pause the video if you're going to solve. But if you want to know the answer, so since we are given the mass of each element, we are going to convert them into moles by multiplying their molar masses and then obtaining their molar ratio. So the empirical formula for this compound is CH3. Lastly, we have combustion analysis. Combustion analysis is a standard method of determining a chemical formula of a substance that contains hydrogen and carbon. A weighed sample is burned in a furnace with excess oxygen, and all of the carbon in the sample is converted into carbon dioxide and hydrogen into water. So for example, a 2.0714 grams containing carbon, hydrogen, and oxygen was burned in a combustion analysis apparatus. 1.928 grams of water and 4.709 grams of carbon dioxide were produced. Separately, the molar mass of the sample was found to be 116.16 grams per mole. Determine the empirical formula, molecular formula, and identify the sample. So for combustion analysis, the mass of carbon is determined from the mass of carbon dioxide produced. The mass of hydrogen is determined from the mass of water produced, and the amount of oxygen is determined by the difference after the carbon and hydrogen has been determined. So for the first step, convert the mass of water and carbon dioxide into mass of hydrogen and carbon respectively. So for the mass of hydrogen, 1.928 grams of water will produce 0.2140 moles of hydrogen, and is equal to 0.2157 grams of hydrogen. 4.709 grams of carbon dioxide is equivalent to 0.107 moles of carbon, which is equivalent to 1.285 grams of carbon. The second step is to subtract the mass of hydrogen and carbon to the mass of the given sample. So 2.0714 grams sample minus 0.2157 grams of hydrogen minus 1.285 grams of carbon is equal to 0.5707, which is the grams of oxygen. This is also equivalent to 0.03567 moles of oxygen. The third step is to calculate the mole ratio to the each of the element to determine the empirical formula. So since the lowest mole we obtained is 0.03566, we are going to divide. You're going to be the it is going to be the denominator. So we will obtain we will obtain 1 mole of oxygen, 6 mole of hydrogen, 3 moles of carbon. Excuse my typos in my presentation. The empirical formula is therefore C3H6O1. So for the last step, we determine the molecular formula. So to determine the molecular formula, it's just the molar mass over the empirical formula mass. So 116.16 grams per mole over 58.08, which is the grams of or the molar mass of C3H6O, is equivalent to 2. So the molecular formula is C6H12O2. And that is all for my presentation.